Good morning and welcome to our lesson. We are still on forces, that is the turning effect of force, and today we want to look at parallel forces. Do parallel forces have any turning effect? Can they do anything? Can they alter the balance of a system? Those are the kind of questions we want to try and seek answers for in this lesson. But just to bring you up to speed, we talked about the turning effect being that effect which is felt when a force produces motion in circular direction. That is to mean that the balance of a system can be altered depending on the magnitude and the direction of action of a force. Now, let us try and start by defining parallel force. And these are forces. They are forces that act in parallel directions. Now, there is need for us to remember that actually force in itself is a vector quantity, and that is to mean that we cannot talk about force if you don't have the sense of magnitude or the size and what we call the direction. Now here, our forces or the direction of action of force is what informs our classification of forces as either parallel or anti-parallel, as we are going to see in a bit. Now here, I want us to take an example of forces on a meter rule. Forces on a meter rule. One could be acting upwards, the other one could be acting downwards around a point, around or about a point, so that this one acts in opposite direction with respect to the other. Now, if you look at the line of action of our force 1 and this one, they are actually parallel. So by virtue of their line of action, their lines of action being parallel, to each other, we therefore term them as parallel forces. Let us say something about their moment. Let us say something about moment of parallel forces. And what I want us to note here is that total upward movement is equal to total downward moment. Total upward moment is equal to total downward moment. But now, this one is a force. Therefore, if we could take, for example, the same diagram that we had earlier, we consider the moment of the first force and that of the second force. Now, if the total upward force and the total upward moment, and the total downward moment, if they are equal, but in opposite direction as shown by the diagram, then from the direction factor of force, then we can also say that the algebraic sum of moments of parallel forces is equal to 0, the algebraic sum. Why do we say that? Because if we take the direction, the upward direction to be positive, then the downwards direction be negative. Therefore, the upward moment is equal to negative of downward moment. Therefore, if you sum them up, they are supposed to give you a 0. They are supposed to give you a 0. Not that they are actually equal to 0, but because of the direction, we cannot take them to be positive. For a vector, direction is very important, and that is why we take one of them to be positive, the other one is negative. The algebraic sum gives us a 0. Now, let us prove that. Let us prove whether what we have said is true by way of example. Now, our question is here. Study the figure below of a meter rule of weight 1.6 newtons supported at the 32 centimeters mark, and the meter rule is balanced horizontally by a 1.2 newtons weight as shown. Now here at the 32 centimeters mark is where we have put our pivot, and on the upper side we have also put a weighing balance. Now, at some point here, which we do not know, we have 1.2 newtons, and here we have a point which is the center of the meter rule, 50 centimeters, and that is where we expect the weight of the meter rule to act now that it is uniform. So question 1, we are supposed to find the point at which the 1.2 newtons is suspended. Now let us try and establish the point where we have the 1.2 newtons. Let us try and establish that. Again, this is the weighing balance. And then from the question, the weight is 1.6. So at the 50 centimeters mark is where 1.6 Newton is supposed to act. Now, we want to find out which point is this. Which point is this? Now, I want us to start by ignoring the weighing balance. Then we can take the clockwise moment as well as the anti-clockwise moment, compare them, and find the value of the point at which our 1.2 newtons act. Now, we have a distance here, which I'm going to call D. The other distance is 18 centimeters. So we could say clockwise moment will be equal to 1.6 multiplied by 18 over 100. And that one gives us 0.288 Newton meters. Then we have our anti-clockwise directions, giving us anti-clockwise moment, which will be given by our distance D multiplied by our force, which is 1.2 D. But no, we just studied the principle of moment, and we said that clockwise moment should be equal to anti-clockwise moment. Therefore, let us compare the two, where 0.288 Newton meters will be equal to 1.2 D. Will be equal to 1.2 D. We can divide throughout by 1.2 and by 1.2, so that our D becomes 0.24 meters, which is equivalent to 24 centimeters. But something I want you to note from the diagram. From the diagram, we had our center here. Then the pivot was somewhere there where we had the wing balance. Then we had the 1.2 here. So the distance from the fulcrum, which is at 32, to where now we have the line of action of our 1.2. This is 1.2 newtons. This distance here is what we have found. This distance is what we have found. But now the question requires us to get the mark. So it means that 32 centimeters minus 24 centimeters is what is going to give us the mark. So you take 32 centimeters minus 24 centimeters, so that now here we will have our 8 centimeters mark, now upon which we have suspended our 1.2 newtons. So what I'm emphasizing is that you're not going to take the 24 centimeters and use it as your mark, because that one is the perpendicular distance from the fulcrum to the point of action of the 1.2 newtons. Therefore, it's only when you take the 32, subtract the distance that is here between them, that you can be able to establish the mark where your weight or where your force is acting. Part B of the question. It requires us to get the reading. This is B. Requires us to get the reading on the weighing balance. The reading on the weighing balance. Now remember, we have the weight of the meter rule. The weight of the meter rule acting somewhere at the middle, and the weight had been given as 1.6 newtons. Then at the 32 centimeters mark is where we have the weighing balance. Then at the 8 centimeters mark, here that is the 32 centimeters mark. Then here we have 1.2 at the 8 centimeters mark. So if we suspend our meter rule using a weighing balance, what do we expect the balance to weigh? Now the balance weighs reading will be weight of the meter rule added to other downward forces. Is actually the weight of the meter rule plus other downward forces, and we have just two, where the weight is 1.6, then we have another force which is 1.2, and our leading will be 2.8 newtons. Remember that force is actually expressed in newtons as its SI unit. Now we want to look at yet another type of force, which we call a couple. A couple. A couple is a pair of forces that are equal, parallel, and in opposite directions. That is actually what we call a couple. That forces are equal, they are parallel, and they act in opposite direction. Now, think of situations that make use of such forces, which are equal, parallel, but in opposite directions. What we want to give as examples of a couple is, for example, forces applied when we are tightening or loosening a nut. Think about what happens when you tighten or loosen a nut. You will be having some two forces, one in one direction and the other one in the opposite direction, though they are equal. That is an example of a couple. How about when we turn a tap on or off? What about when we turn a tap on or off? We also apply equal opposite forces, though they are parallel. They are in opposite direction, but they are parallel. You can also talk about when we are steering a car. When you hold the steering of a car, you apply forces on opposite directions. And finally, is when a cyclist turns. Well, a cyclist turns. They could be more than that. You can think about some, but these are just but a few examples of the forces that will involve, or activities that will involve a couple of forces. Remember, we have defined a couple as a pair of forces, a pair, not more than two, a pair of forces that are equal, parallel, but in opposite directions. Let us look at moment of a couple. See what we can say about moments of a couple. Moment of a couple, because if they are two and they are acting about a point, then moment results. But let us use an illustration here. Put the pivot somewhere there. This is the pivot. Then we have the pivot there. We have one force, F. Then we have another one here. And we want the two forces to act about the pivot. Now, this distance here, let us take it to be D. Then this one is L. Can call this one force. We have said they are equal, so we can call all of them F. And the other one is F. Now, the whole of this direction, that is from the line of action of the first force to the line of action of the second force, the perpendicular distance between them is D. Now, if from the pivot to F is L, then this other one should be D minus L. It should be D minus L. Now, let us look at the moment of the two, and we say clockwise moment will be equal to F times L. Now, anti-clockwise moment, on the other hand, will be our distance, which is D minus L. We multiply by F. Multiply by F. We can go a step further and open the brackets so that we will have FD and then minus FL. FD minus FL. Now let us look at total moment. Total moment will be clockwise moment or anti-clockwise moment plus clockwise moment. Now remember that moment is given by force and the perpendicular distance from the point of support to where the line of action of the force is actually located. Now, anti-clockwise moment is FD minus FL. We add that to the clockwise moment, which is FL. So that now FL goes with the other one, and we are left with FD. Now, we started by looking at the forces. We said they are equal, parallel, but opposite. Now, we took the distance between them to be D, but somewhere at the middle or somewhere in the setup, we placed our pivot. Now, from the pivot to where one of the F's is acting, we took the distance to be L. So that now the remaining one from the pivot to the second F will be D minus L. Then we took the moments individually, so that clockwise moment was now force times the distance from the pivot, which is F times L. And clockwise moment equally was given by the force times the distance from the pivot to the line of action, which happened to be D minus L. When we are looking for the total moment of the system, we add the two where we cancelled FL because we had a positive and a negative FL, and we resulted with FD. Now, the point I'm trying to make is that moment of a couple is given by one force multiplied by perpendicular distance between them. Remember that a couple of forces exists as a pair of equal, opposite, but parallel forces. Now, if you take the distance between them and you multiply by the magnitude of one force, you are going to get the moment of the couple. Let us look at an example. There goes our question. A couple of forces act on a meter rule at the marks given, the 12 centimeters and 80 centimeters marks respectively. Now, if each of the forces has a magnitude of 3.6, we are required to calculate the moment about the 28 centimeters mark. Probably we begin by making a sketch of the couple of forces. Now, there goes our sketch. Now, we have the forces each having a magnitude of 3.6 newtons, and we want the moment about the 28 centimeters mark, this mark here. Now, but we have said that moment is given by one force multiplied by distance between them. Each one of them has a magnitude of 3.6, and the distance between them, this distance here is given by 80 minus 12, which is 68 centimeters. Therefore, the moment will be 3.6 newtons multiplied by the distance, which is 68, divided by 100. Which gives us 2.448 Newton meters. I want us to verify our answer by taking the clockwise and the anti-clockwise moment and adding them together. So we can consider each of the forces individually. Can consider each one of the forces individually. I take clockwise moment. Clockwise moment will be given by 3.6 newtons. And this one we multiply by 62 over 100. That is 80 minus 28. It's 52. 52. So that this one gives us 1.872 newtons. That is the clockwise moment alone, is given by the magnitude of the force. You multiply that by the perpendicular distance from the point of support, which is the 28 centimeters mark, to the 80. You get that distance. Now, anti-clockwise moment will be again 3.6, and we multiply by the distance, which is 28 minus 12 divided by 100. This gives us 3.6 multiplied by 0.16, which is going to give us 0.576. Again, these are Newton meters. Then let us look at the total moment. The total will be given by 1.872 plus 0.576, which takes us back to our initial answer, which is 2.448 Newton meters. Therefore, whichever way you choose, you arrive at the same answer. Of great importance is to note that if you are talking about a couple, just take one of the forces and the distance between them. That one will suffice. Let us look at another example. Now, we are supposed to consider the forces on our diagram here. We have F1, again we have another one, F2, and determine whether they are a couple. So we start by getting the value of their magnitude, then find out whether they are a couple. Let us start by considering F1. And I want us to take moments about A. Moments about A. And at A, we have this distance 0.8, and we have a force of 3 newtons. So we have these 3 newtons. The distance from 3 newtons to A is 0.8, and again you realize that the distance is actually perpendicular to the line of action. Now, 0.8 meters, we multiply by 0.3 will be equal to F1, and we multiply by the distance from the line of action, which is perpendicular at A. So we will have 0.6 and F1, then 0.8 and 3. And from there, we can divide by 0.6 and divide again by 0.6, so that F1 is equal to 4 newtons. The F1 is equal to 4 newtons. Note that we have looked at the perpendicular distance. This one is 3 newtons acting in this direction, but we are taking moments about point A. That is why we take this to be the distance which is perpendicular to the line of action. Now, for F2, we take the moments about C. We take the moments about C, And again, about C, we have this force, which is 3 newtons. 3 newtons moments about C. We have our 3 newtons. Its distance is not changing, so 3.0 newtons. And this one we multiply by 0.8. Again, look at F2. It's acting downwards, but then this one is the distance, the perpendicular distance. F2 is acting downwards. This is the distance which is perpendicular to the line of action, and we have been given as 0.6. So 0.6 times F2, and this one implies that F2 equals 4 newtons. Now, we have been able to calculate the magnitude of the two, but then the question does not end there. We are also required to determine whether the two forces, that is F1 and F2, whether they are a couple. And if they are, we should also give reasons for our answer. So now, to the part B of the question. Number 1, F1 and F2 are equal. They are equal. Then we look at their direction. We say that F1 is opposite F2, and number 3, are they parallel? Their lines of action, we have this one and this one, and the lines of action are actually very parallel. Lines of action are parallel. So, the two forces, having satisfied the 3 requirements for a pair of forces to qualify to be a couple, then we say yes, F1 and F2 are actually a couple. They are actually a couple. Let me give you the last bit, which is applications. Applications of a couple of forces. Application of a couple of forces. And number 1 is steering a car. We have opening or closing a tap, opening or closing a door. Those 3 are actually the applications of a couple of forces that we have. Let me give an assignment, or rather some questions that you should try and look at in an endeavor to make your mastery of this content a bit high. Question number 1. Define a couple of forces. That is the question number 1. Number 2, show that moment of a couple is given by one force multiplied by perpendicular. Distance between the forces. Number 1 requires you to define a couple of forces. Here, just to hint, I want you to look into the equity, direction, and the fact that they are parallel. And again, do not forget that if you want to talk about a couple, it is just made of 2 forces only. Now, we want also to show that the moment of a couple is given by the product of one of the forces and the distance between them. We have just done that. You use the illustration that we established. You use that illustration and then you resolve the moments. That's all about moments of a force and the turning effect of a force. Next time we meet, I will look at the equilibrium and center of gravity. Another topic that will help us to really answer very many questions that we have in our minds. Thank you.